Chapter 10, Gas Power Cycles. All right, everyone, today we're going to talk about gas power cycles, and I will explain it like a simple story with examples you can relate to. Imagine you have a toy car that needs energy to move. You fill it with batteries, or maybe wind it up, and it runs in loop. Power cycles are just like that. They are systems where energy comes in, makes something move or produce power, and then the cycle starts all over again. In big machines, like car engines, power plants, or even airplanes, we use power cycles to turn heat into motion or electricity. Now, in this story, we have two types of cycles. One is called the gas cycle, where air stays as gas the whole time, like the air in your bike tire. Another is vapor cycle, like steam from a kettle that can change between liquid and vapor. Today, we're focusing on gas cycles, like those inside cars, motorcycles, and airplanes, where the working fluid stays as gas. Let's pretend our toy car has two ways to get energy. One is by burning fuel inside, called internal combustion, like car engines. The other is by heating something from the outside, called external combustion, like an old steam engine train. Internal combustion is like cooking noodles inside a pot, and external combustion is like using fire under the pot to heat the water. When engineers design these systems, they want to keep them simple to understand, like drawing a cartoon version of a real car. We call this ideal cycle, where we remove things like friction and make things happen perfectly. This helps us understand the main idea without being distracted by small details. One example of an ideal cycle is the Carnot cycle, which is like the superhero of cycles, the most efficient one you could dream of. But in real life, it's too slow and complicated to build because it needs too much time and perfect conditions. So, we use other cycles like Otto cycle, diesel cycle, Brayton cycle, and Stirling cycle, which are like the cousins of Carnot, easier to build but still good at producing power. In car engines, for example, the Otto cycle is the star. It has 4 steps: squeezing the air and fuel together, igniting it to make it explode, letting it expand to push the piston, and then letting out the used gases. This is like how you pump air into a balloon, pop it, let it blow up, and throw away the rubber. Diesel engines are a little different because they don't use a spark plug. They squeeze air so hard it gets very hot, and when fuel is injected, it burns automatically. That's the diesel cycle. Gas turbines, like those in airplanes, use the Brayton cycle. Air goes into the engine, gets squeezed, then fuel burns in it to make it very hot, then it expands quickly and spins the turbine to make the airplane move. To make engines more efficient, engineers use tricks like regeneration, which is like recycling leftover heat, or intercooling, which cools air before squeezing it again, or reheating, which burns fuel in stages to keep the engine powerful. In each of these engines, we want to know how much useful work we get and how much heat we waste. We calculate efficiency, which is like a scorecard, showing how much of the energy we use actually turns into useful power. Perfect efficiency is impossible, but by using good designs, we can get close. In summary, gas power cycles are like fun little races where air is the runner, fuel is the food, and we want the runner to go as far and fast as possible without wasting energy. By understanding these cycles, we can design better engines, make cars go farther, airplanes fly longer, and power plants give us more electricity. That's it for today. Next time we'll have fun looking at these cycles with numbers and diagrams.